Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Today we will come out of hands-on session, and for this entire week we'll be taking up something about thermodynamic assessment, and this week is about the outline of this thermodynamic assessment and how the input data are taken for this particular process. This is basically, as you know, to generate Gibbs energy data. So let's see how to do that. These are going to be the content for today's class. We'll see what is curve fitting in general. This is going to be there at the core of this thermodynamic assessment process. So we'll see what is this curve fitting process in general and what is the input for it and what is called modeling in it and the output of it. Okay. Then we will see how the curve fitting is done in CalFET, and here also the same things, input, modeling and output are there. So we are going to understand what is Gibbs energy modeling based on this. Okay, this is going to give you a very simple picture of that, and then we will see what are the names used for this process, and the name that we are going to use is called thermodynamic assessment. We will see some details about that and start seeing the different types of input data that is required for this process. This is curve fitting in general. What you see here is three different graphs, but if you carefully see what are these different data points, these are some 15 different data points, how y depends on x, and the same 15 data points are repeated in the all three cases. And if you see this orange line here is the one used to fit. Okay, basically this is going to tell you the relation between y and x, and is it a straight line relationship or a more complex relationship like the case 2 or case 3. Okay, so this choice of this line is up to us. As depending on the choice of the line, you can get a better and better fit. Okay, you can see case 3 seems to be fitting much better, but the relationship between y and x seems to be very complex. In the case 1, it is very simple, a straight line relationship. You can see something like y equals mx plus c kind of a relation here. So this is the dependency of y on x, and this seems to be very simple, but obviously you can see the error here is quite significant. From each data point the fitted curve is quite far. Okay, so this is polynomial fitting with increasing order for the same data set. Okay? If you see, this is mx x power 1. Okay, so this is order 1, and you can choose something like order 2 or 3 here, and even higher order here. This can look like ax cube plus bx square plus cx plus d, something like that, a higher order fitting. Okay, so this is what we have seen. Input is going to be data points for curve fitting and data on how y is related to x. Okay, when we go to Gibbs energy modeling, we will see that how Gibbs energy is related to many other properties. And the model, when we say model, the chosen equation is the model. When people talk about modeling, some people think that modeling is something too different and it's not something they're going to understand easily, especially people who work completely on experimental kind of work. They think that modeling is something else. Okay, but modeling is nothing but, in this case, the chosen equation. Okay, the straight line model is used in case 1, y equals mx plus c, and m and c are model parameters. In the equation, you will call it as coefficients, right? So here m and c are model parameters. So this is a different terminology we are going to use. For equation, we are going to use the word model, and the parameters here are called model parameters. Okay. So once model is chosen, then we can fit. Best fit needs to be figured out by adjusting the model parameter values. So you have decided, let's say, a straight line you are going to use to fit it, and what should be the value of m and c, and that is going to decide the best to fit. Okay, for example, least square method can be used. What is least square method? You can think of it like this. If you have a curve which is fitting these data points, the distance between the original data to the fitted curve, in one case the dot may be above the line, the other case dot may be below the line, the experimental dot, let's say. The distance between them you can measure and square that. because one case it is positive, in the other case it is negative. The distance between, that is the error. Okay, the error you can square, and through that you can figure out how good is your fit. Okay, so that is called least square method, and best fit needs to be figured out by adjusting the model parameters. So the job here, when we say fitting, we are basically adjusting the model parameters. We are adjusting the m and c values to get the best fit. Okay, that is fitting part. Once fitting is done, we get the output. Okay, once model is fitted to data points, m and c assume some numbers. Okay, description of the y in terms of its dependency on x, basically the equation for y equals 5x plus 2, for example. Okay, this is how you get the final output. This is called as description. Now in CalFAD, similar structure is there. Input data points are going to be any data on how G is related to temperature, composition and pressure. Okay, so any data in the sense, enthalpy can be related there, activity can be related there, entropy can be related there, Cp can be related there, chemical potential can be related there. So multiple things can relate to G. When T, X and P changes, all those things change and G changes, right? So these are the different data points we are going to give as input for CalFAD based thermodynamic assessment. Now model is going to be the chosen equation, as we said before, with some extra things called formalism. We will see about that later. Essentially it is the equation that we are choosing. Okay, for example, RK polynomial, it's going to be a polynomial fit called Redlich-Quista polynomial. We have seen about that previously. Delta G XS mix is modeled like this. We have seen this XA XB, then summation over nu equals 0 to n and nu LAB XA minus XB power nu. Okay, we have seen this, and we said this LAB are called model parameters, right? So this is the equation we choose to fit Gibbs energy as a function of these different things, right? And fitting is going to be again best fit needs to be figured out by adjusting the model parameter values. We can use methods like such as least square method, and the output is going to be this. Once model is fitted to data points, model parameters assume some numbers, and from that we are going to get Gibbs energy description. We have seen few Gibbs energy descriptions before, the SGTE data and all I showed. That is going to be Gibbs energy description. Ultimately, we are going to combine that and put it into a database files form. Okay, we have used databases and made several calculations, and this is how the Gibbs energy is arrived. This is a very simplistic picture of what is happening here. The names of this entire process are these. Different names are used in literature: thermodynamic assessment, thermodynamic modeling, Gibbs energy optimization. Sometimes the output is published in the name of thermodynamic description of so and so alloy system, things like that. Okay, so these are all same things. We are going to continue with the term thermodynamic assessment, right? So this is what thermodynamic assessment is. Make suitable Gibbs energy models and fit them to critically assessed input data, not any input data, critically assessed input data to get Gibbs energy descriptions. Goal of the assessment is to get the Gibbs energy description of phases, right? So this is what we are going to do. So let me tell you now itself, this upcoming 5 lectures and the next 5 lectures are going to be more focused on this thermodynamic assessment, which is going to give us the Gibbs energy description and how the databases are made. These topics may not be of interest to many of you, because many of you will be interested in how to use the databases, how to use the CalFED tools like ThermoCalc and do something for your work, and not getting the Gibbs energy description itself. If the database is not available, you are not interested in generating that, because that's going to be a more tedious process. You can leave it to CalFED experts and only focus on using the Gibbs energy descriptions. So if that is your intention, this about 10 lectures or so, you can take it slightly in a milder way, because I am trying to keep it as much as possible quite generic. I don't want to make it too much of expert teaching to PhD scholars of this particular domain. I want to keep it little more general and trying to introduce you to most of the things here, and rather than going much deeper into each of them. Let's see the brief outline of this method. Okay, so you can treat these the three different things. These are the three different major activities that are going to be there in this. First is input data. Any data related to Gibbs energy, enthalpy, entropy, heat capacity, activity, chemical potential, phase equilibria data, all these data which are related to Gibbs energy can go as input data. On the other side, we have model where Gibbs energy models for composition, temperature and pressure dependency. G dependency on composition and temperature will be of the focus mostly. And then with suitable formalism, this is an extra information which we need to keep in mind to model. So we are keeping the models, the equations with A plus BT, CT, LNT kind of ABC values. We are going to keep the models on one side. And then we are going to fit the models to input data so that the TABC will assume some numbers. Okay. So this is called a statistical fitting or Gibbs energy optimization. And here models are fitted to input and the output is going to be Gibbs energy description. So these are the three major things we do when we created a thermodynamic database through thermodynamic assessment. These are the different files. Input file is called pop file.pop file. Setup file where the models are is called the .tcm file. The extension it's called a setup file. And then the optimization where the curve fitting is done in this file called .par file in thermocalc. The module used for this purpose is called parrot module, parameter optimization module. The file used there is .par file. This is usually going under the hood. We will not be able to see this when we do the optimization. Then output file is going to be the .tdb file, is the thermodynamic database file. In future, we will see a detailed outline of thermodynamic assessment. The what we have seen in the couple of slides previously are a very brief outlines. Okay. So now let's focus on this input data part. This is going to be covering a few lectures now. And there are two major types which we'll be focusing on. That is thermodynamic quantities, especially thermochemical data, and the constitutional data, which basically tells you what are the constituents of the material. Basically the chemistry of phases, what phases, how much of these phases, things like that. That is constitutional data. The other words, we call it phase equilibrium data or phase diagram data. Okay, so we'll focus on one by one. First, the thermochemical data, especially enthalpy, entropy and activity and all, they can come from multiple methods. So the outline is given here. Common experimental methods are here: calorimetric method, gas phase equilibrium methods, electromotive force, EMF measurement methods. And then common theoretical methods are there, methods based on physics, quantum physics, statistical mechanics, classical mechanics, and then some semi-empirical approaches. These calorimetric methods will focus. So if you think about calorimetric methods, calorimeter is basically a device where you can monitor energy exchange, the temperature and time. Okay, you give some energy, see how the temperature is going up, is there any phase transformation taking place, all those things you can monitor. That is basically calorimetry. So let's focus on what are the different things we can get from this. First thing we will see is enthalpy change. Enthalpy of the product or products minus enthalpy of the parent or parents. The determination through calorimetric methods. First thing is heat of transformation. Delta H is there for many processes. We will see delta H transformation now. This is figured out from differential scanning calorimeter or DSC. Okay, I'm not explaining the entire principle and things in that. What it does essentially is this heat evolved or absorbed Q during a transformation, for example melting, is measured and the pressure is going to be constant. Therefore, whatever heat exchanged is equal to the enthalpy change. Okay. That is heat of transformation. Then there is heat of reaction, which can be done using direct reaction calorimetry. And here inside a calorimeter, a mixture of powders of the pure elements is quickly heated in a small furnace until it reacts to form a compound. So when the compound forms, heat evolved or absorbed during the reaction is measured as delta H. That is heat of reaction or enthalpy of reaction. Okay. This heat of reaction for certain reactions such as combustion can be done in combustion calorimetry. Things like bomb calorimeter can be used for this purpose. In this combustion calorimetry, the sample is ignited and it reacts with reactive gases such as oxygen or fluorine to form oxide or fluoride. So this will be a highly exothermic process, and the heat evolved or absorbed during the combustion is measured as delta H. Okay, then we have heat of mixing coming from solution calorimetry or drop calorimeter, where a compound is directly taken, AB, let's say solution directly taken, and is dissolved in another solution. Okay, and the lattice structure of it breaks. Structure of this compound or solution breaks when it dissolves into another solution. Individual elements A and B are also dissolved into the same solution, let's say Z. Okay, these are separate dissolution experiments, and heat evolved or observed during the dissolutions of all these things A and B are separately measured. Okay, and then the difference in the heat of dissolution, Q dissolution of AB minus Q dissolution of A minus Q dissolution of B. Okay, the product minus reactants basically is estimated as enthalpy of mixing or enthalpy of formation of AB from its elements. Okay, how it works, why it is right, all those things you can explore further. We are not going into the details of it. Okay, then there is CP measurement, the heat capacity measurement. Okay, heat capacity is heat required per unit temperature increment per unit mass or 1 mole. Differential scanning calorimetry or adiabatic calorimetry can be used for this. Heat exchange during heating or cooling is measured. The pressure is kept constant. Therefore, what we measure is Cp, del Q by dt, and delta H, enthalpy with respect to a reference state, wherever we started from, can be measured from, let's say, low temperature to high temperature. Low temperature will be called as reference state value. Integration Cp dt will give us delta H. If the Cp is for a particular phase, then you get delta H for heating that particular phase. Right. So more resources for calorimetry are given here. There is an entire book on differential scanning calorimetry. Okay, the textbook suggested for this course also has quite extensive coverage of these different techniques. Thank you. I hope the lecture is useful. See you in the next class.